Hello, everyone. Come on in. Does anyone have any questions before we get fired up? Ready to roll, that sort of thing? Can everybody hear me? You hear me, Nick?
Yes.
Good deal. Okay.
Yeah, we can hear you.
All right. And we're up to 14 people in the class now. And no one has any questions, past material or otherwise? I think I went into my lab in mastering and noticed some problems with the dates for chapter 23 and repaired that. Y'all might have noticed. Did anybody notice whether I had? I know I did it for my other two classes. I think I did it for yours as well, but I'll double check real quick while I'm here. And you know, the actual test is now up. You have until Sunday night, 11:59 to get all your attempts done on test 1. The practice test, of course, for test 1 and test 2 is still up. Practice test 1 will disappear when actual test 1 is due. I'm looking at the dates now. Today's the 26th, and yes, 23 I moved to the 30th for conceptual, and 24 to February 6th. And then the actual homework problems, 23 is due on the 1st of February, and 24 is due on the 8th of February. So yeah, I did do that change. So hopefully y'all noticed that before you had to waste a lot of time. One thing I want to recommend to you guys is in my last 2 PHY 242 classes, the D01 B1, I've actually did some more integration problems to calculate electric fields. So you might want to check out the videos from those classes, at least the examples in it. You know, scroll through and find me working an example and then watch me work it. I had some problems uploading some of the videos I made, so I ended up doing it again in class. But anyways, like I did the I did the ring of charge. I calculated electric field of that, and I did the disk of charge. I thought I found an error in it compared to the way the book did a similar problem. I'm not convinced that it is, but I wrote on that. If anybody wants to figure out what error I made and make it, you know, mesh with what the actual book had done, then you can turn that in for extra credit, and basically it'd be like 100 for an extra homework assignment. So, and you know, everybody basically, once I add that, everybody will get, instead of 2 dropped homeworks, you'll get 3, or instead of 1, you'll get 2, whatever I said on the syllabus is being the 1 or the 2 that I'm going to drop. But now it'll add 1 more to it because it's got extra credit. So you'll get a 0 on it if you don't do it, but that won't harm you because, like I said, I increase the number that's being dropped by 1. So definitely check that out on my YouTube channel. Don't refrain from looking at 242 other classes, in other words, specifically ones around the same date, like 120 and 125 and stuff like that, so y'all can see more stuff. Anybody have any questions before we get started? I'm going to do chapter 24, jump into that today, let you get the hang of it, and hopefully you'll be able to start doing that kind of stuff and be ready for chapter 2, because remember, every 2 chapters I'm going to have an online test. And I like to do it that frequently because I find out the grades become more normally distributed. And actually the grades in general are overall better because you guys are testing a lot more often, between taking all the practice tests and then taking the 3 attempts at the actual online test. You get to solve a lot of physics problems. So the more physics problems you solve, the better off you get. And you've got then homework, conceptual homework, practice tests, and actual test attempts. All of those are more problems to be solved, and you're starting to approximate what I used to work, which is on the order of 30 to 50 problems per chapter. So that's a very reasonable number. It sounds like a lot because you guys probably aren't used to that much. Maybe you were in calculus, maybe not even then. I've met a lot of calculus teachers that only sign a couple problems a night, but yeah, you need a lot more practice to do this stuff. So since it appears no one has any questions or anything, I guess I'll just go ahead and start talking about chapter 24, capacitance, dielectrics, electric energy storage. That's what the chapter is called. Let's start by sharing my screen. So for starters, you can look right here and see that this is my studio page where my YouTube channel is. But you can see there's problems up here. This is 242. This is a video from D01B from 125. That has some good material on it. There's another one from D01B from 125, and I have no idea what. Oh, that's 241. Never mind. Now I have an idea. Here's your video from 124, which was the night before. So your videos are up here. My videos are up there. I'm actually getting them uploaded a little quicker than I normally do. I usually don't always get them to the next day. Lately, I've been getting them the same day, at least by that night. So anyways, y'all can check that out. What I'm going to turn back to now is this page, which just is all the dates we were just looking at. I'm going to go back to the main menu, and I'm going to go back to the e-text. And what I'm going to pull up here is the opening page of chapter 24, just so you can see what capacitors look like. And I'll tell you a little story where basically I saved myself a buttload of money by having just an easy bit of knowledge. So let's say access my e-text. And let's see what comes up. A black page. That's perfect. Perfect. But it's really going slow. By the way, Pearson does have an app now that works pretty well, like on an iPad or a phone. So I'd highly recommend you using that to access your e-text. As you can tell, this is super fast. I guess I shouldn't have been doing it this way, but anyways, it's a little more convenient. So what a capacitor is sort of like a battery. It's like a battery in the sense that you can charge it up like a battery, and then you can run all the charge out of it, which is sort of what's going on when you wear down a battery, but you can immediately charge it back up, and you can dump the power or all the energy out of the battery really, really fast. So if you've ever used like a 35 millimeter camera with a flash, you'll take a photograph, you'll hear the flash go pow, pow, like it, really makes a pretty distinct noise. And then you'll hear a whistling noise, and it gets higher and higher pitch, so like that. That's actually it charging up a capacitor. So that gives you some idea of what capacitors are used for. Capacitors really are another power source, but they can do it a lot faster, and they're a little more reliable than a battery, in that a battery has a limited number of times you can charge and discharge, charge and discharge. Whereas a capacitor technically has a limit too, but that limit is way, 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 way higher than the limit for charging and discharging batteries. This is some of the last stuff we did in chapters 20 and chapter 22, which is where we covered, whoa, why did it go here? Okay. It's supposed to go to this page. Where we covered voltage, and then we used the integral equivalent of the voltage equation, which is sort of like the equivalent of Coulomb's law. So instead of it being vector, which we had that really complicated expression that dE is equal to the dQ times parentheses RP minus RdQ close parentheses over 4 pi epsilon naught times the magnitude of RP minus RdQ vector, and then that magnitude was cubed. That was the Coulomb's law version for electric fields. But for voltages, since they're scalars, we got that really nice expression, which was basically just dQ over 4 pi epsilon naught R. no vectors whatsoever, makes life really easy. So this is, for some reason, it jumped right to section 24.2, even though I said I wanted 24.1. And actually, I want to see the opening page of the chapter, but it's just doing its own thing right now, and we're all just tickled about it. So it's not the most useful version of an ebook. I'll just say it that way. But like I said, I've loved Ian Coley's book for a long time. So here's some typical pictures of capacitors, and this is the main reason I showed it to you. This actually looks quite a bit different from the opening picture in my copy of the 4th edition of Ian Coley. This is the look that I'm used to, is more this little sphere, this little cylindrical look right here. And usually if you look on the top of that, there'll be like a little Mercedes symbol. In other words, it's got 2 bars like this and 1 bar going up. And that actually, if you ever see a capacitor that has that little thing popped up where there's 3 lines for the Mercedes symbol that broken loose right there, it'll show like opened up at the Mercedes symbol, then you know that capacitor is blown. And that's what I was telling you about regarding a story where I saved a little money. When I worked up until 9/11, I had been recruited from an engineering company out of my PhD program at Chapel Hill. I was waiting to see what was going on because I was having some difficulties with my PhD advisor and the school, sort of, just because he sort of left and didn't take his grad students with us with him or anything like that. So I was looking for a job just to see if I might need to run out of the PhD program because I was getting ready to be orphaned. I got a job working at an engineering firm in Research Triangle Park. And when I got that, it was like I came in, I was like, I made all these big plans. I knew how much money I should make. And I'm like, okay, I'm going to get, no less than $60,000 what I'm going to take. And they like offered me 80 full medical, dental, and vision insurance for me and all my family. They said they would continue paying for me to get my PhD if I wanted to continue that. I was like, okay, never mind, I'll take it. So I didn't even have to negotiate. But I was making so much money, and it was a really big deal. I went out and bought a HD TV. And it was like they were brand new then. This is, really, really new stuff. And I bought one that was 56-inch or 53-inch or something pretty big for the time. And it cost like $6,000. Really a wonderful TV, but it's sucky compared to a $300 TV nowadays. But either way, about 9 years ago, that TV just stopped working one day. And I called a guy to get it fixed. He's like, oh, it'll be 175 just for me to look at it. And that's if you bring it here. If I have to come out there, it's going to be another 50 and all this stuff. And I was like, oh, this TV's probably not worth that much, but my kids loved it to play their video games on. So I just opened it up. And by the way, be careful with that. Just because you unplug it, it does not mean you're safe. Okay. Because these little things specifically are part of the problem. These capacitors can hold on to charge long after you've unplugged the device. So you literally can get electrocuted, and that means shocked to death, even though you've got the power off. But I knew enough because I'd done a little bit of electrical engineering, and I looked, and lo and behold, there was a blue and gray capacitor, blue with a little gray stripe down the side, a polar capacitor. It had a positive, negative side, and it was shaped just like this. And I looked, and that little Mercedes symbol cap had busted open, and I was like, I wonder. So I cut that sucker out and I looked, it just happened to have exactly the same capacitor in my little kit of tools that I had from teaching electronics at Chapel Hill. I soldered it back in and it worked perfectly for another 9-10 years. So that's the kind of advantages you get from having some experience. Just like I said, be very careful. I would not say take your calculus 2 or your calculus-based physics 2 and start repairing TVs. I would not say that, but if you have some extra experience in electronics, knowing these things can actually help you a lot. So they normally look like this. A lot of them look like this as well. Some of them look like these other guys. This one's actually a variable one, and you see it's got that long arm sticking out of it. That long arm normally is attached to a rod, is attached to a knob. And that rod, when you rotate the knob, the rod rotates and it makes the capacitor have a larger section of faces interacting with each other. So basically they're turned and they're pretty much the same shape, but maybe they're a half circle. And when you turn them like this, part of the half circle isn't across from the other part of the half circle. So they're less capacitance. But as you turn it the other way, when their whole faces match each other like this, then you actually get more capacitance. Doing that, you can adjust the capacitance of your radio station, of your radio, and that sets up more or less a way of picking up a specific station. because there's circuits that tune to certain stations based on their RC value, which is their resistance times their capacitance. So by adjusting the capacitance, that actually allows you to tune into a specific station. So that's why you see them a lot of times like that. But they're really good. Like I said, their main goal is to store electricity, store energy, store power, and you'll see that they do in fact store energy. We can calculate exactly what that is. The simplest version of a capacitor is just a plate and then another plate, and then one of the plates will be positive charged and the other plate will automatically become negatively charged by the exact same amount, and they have to have a space between them. Okay, a small space usually. And we learned about, for instance, how two charged plates like that next to each other but of opposite charge will actually have an increased strength of electric field in between them. And since they're close together, in fact, the electric field will be treated as if the plates are infinitely large. In other words, the plates will have an electric field that seems to be independent of how far away you are from it. So, and we're going to see that again today, but that's the most typical example of the simplest type of capacitor you can have. In fact, the surface area of the plate is relevant to the capacitance value, which we measure in farads, by the way, and the distance between them. That too is a measure of or a parameter that dictates the capacitance value, and whether it's filled up with air between them, or whether it's filled up with a vacuum or mica or some other what they call it a dielectric, but basically that's a fancy word for a insulator, a non-conductor. So you can put that non-conductor between them, and that does a couple things. One thing, it keeps the plates from bumping against each other. You know, you can imagine you're probably going to either want a big area and a small distance apart, or you're going to want a huge distance apart or a big area. Y'all don't know that yet. We're going to find out in a second. But either way, once you start trying to manipulate those things, the geometry and its ability to stay together can be affected by things like the distance apart and stuff like that. So you might think it would be better to not have these two metal plates separated just by air. And in fact, that's an advantage of putting in a dielectric, is you can actually take the dielectric, put it in the center, and of course it'll be in the middle, and then you'll have this plate pushed up against one side of the dielectric and this plate pushed against the other, and then you can even take and roll them up and make, you know, something that's a really big area, make it into a small area. Not only that, it actually decreases the electric field in it, so it lessens the chance that the actual dielectric, the insulator, will break down and become a conductor. So for instance, we all know air is a insulator. You probably know that you can't just make electricity go from point A to point B unless it has a huge amount of voltage. So it can't just go across the air. That's because air is a pretty good insulator. But if you get the voltage large enough, then you can see sparks stretching, say, from your fingertip to a doorknob. And that comes from, you know, charging it up, your finger up high enough so that the air between your finger and the doorknob is close enough that it fails as a insulator and becomes a conductor, and a little lightning bolt will strike. So that happens with capacitors too, because obviously you're going to have them separated by some distance apart, and lightning can strike across that. But by putting the dielectric in there, you actually decrease the electric field and therefore make it harder for the quote unquote dielectric insulator to fail. So that's a lot of cool stuff about it. But you can see there's a lot of things they're used for. You can use them to make the keys on a keyboard work, all sorts of good stuff. Let me turn to the next page. You can see we're going to cover capacitors, determination of capacitance, capacitors in series and parallel. Then we're going to start treating dielectrics, and even going to talk about on the molecular level what happens within the dielectric when you apply an electric field to it, and how do we account for that. So this is what I was talking about. So you have a face A of surface area A, another face of surface area A, and you put them next to each other. You'll find out that the bigger the area, the larger the capacitance, and the smaller the distance between them, the larger the capacitance. We're going to show that in a little bit, but that's what we ultimately find out. And because of that, we want areas to get really big. So if you put something between them, it'll allow you to roll it up like that. So that's what I was talking about, how the dielectric can be helpful. These are the symbols for dielectrics. Normally it's just two vertical lines, or they could be horizontal lines. If the thing was in, say, this left-hand wire of this circuit, you put two horizontal lines of the same length, whereas a battery, remember, has one long one and one short one. This has two of the same length. Sometimes they'll have like this, or they'll have an arrow drawn through it, and those usually mean that the capacitor is not only a capacitor, but it's a polar capacitor, meaning it has a specific negative side and positive side, and if you connect it backwards, it's not going to behave the way it's supposed to. So they normally do that with by showing one of the sides curved, or by throwing an arrow, drawing an arrow on top of it, or something like that. So this is what a circuit would look like with a capacitor in it. Here's a little battery, and here's a little capacitor. Now, what you might imagine, we're pretending we're dealing with conventional current, which is positive charges flowing from the positive side of the battery and then trying to come into the negative side of the battery, even though we know really it's electrons going the other way. We just work with conventional current. Now, what's going to happen there is the positive side of this battery is actually going to establish an electric field that sort of sticks inside of this wire, because this wire is a conductor. It sort of hones along the wire, and in fact comes back towards the electric field, or excuse me, back towards the negative terminal. And that electric field is going to compel positive charges to run around here. Now, what happens when it gets to this face is those charges just distribute on the left face of the capacitor. So you can see the left side of the battery is positive, so the left side of the capacitor will become positive. And then all those positive charges are going to compel all the positive charges in the other face to run away, because like charges repel. So all the little positive charges on this face are going to run around here and go through the battery, and then this face will become charged with a charge negative Q. So that's really how the capacitor works. It's always going to have a plus Q and minus Q, and the magnitude of that Q is called the charge on the capacitor. If you were to take a voltmeter and plug the red terminal onto the left plate and the black cable or black terminal of the multimeter onto the right plate, it would read a voltage V, and then lo and behold, the equation for capacitance is C is equal to Q over V. Your book's written it as Q equals CV, but I like to introduce it as capacitance equals charge over voltage. So your book says, I'm going to write it like here, and then I'm going to show you the page in a second. So Q equals CV, but I define capacitance as the charge applied divided by the voltage, and I'll show you that in a second. One thing I want to remind you is the unit of capacitance is the farad. And that's short for Faraday, I guess you can see, for good reason. And the Faraday is actually defined to be 1 coulomb per volt, which is a huge amount of capacitance. A coulomb's a buttload of charge. As I told you, it's not unreasonable to have, you know, a couple hundred coulombs of charge transferred in a lightning strike. So you can imagine a whole coulomb being in a capacitor just with a voltage of 1 volt across it. You can imagine that's a big deal. So a 1 farad capacitor is in fact a very strong and very dangerous capacitor. In general, when we have these capacitors like laying around in a shop, if it's on the order of, you know, a whole farad, or even, you know, a 10th or a 100th of a farad, we always keep them with the 2 probes, the 2 wires tied together with a conductor, specifically so they don't accumulate charge over time. Because if you got a 1 farad capacitor filled up with charge over time and you accidentally cross them, you could literally be killed. So all right, now that we have that, you can see, of course, we normally use prefixes like pico and micro and nanofarad and that sort of thing. That's specifically because a farad's so big. So I'm going to go ahead and stop sharing and talk about the actual process of calculating capacitance. So let me turn on my document cam. Does anybody have any questions so far about this farad stuff? Okay, so the typical capacitor circuit would be, there's a battery, and then there's the positive end of the capacitor, and there's the negative end of the capacitor. And again, like I said, this is the positive end of the battery, this is negative. So this would have a charge plus Q, and this would have a charge minus Q. And I explained to you how basically this abundance of positive charges are the source of an electric field, that is the battery, is going to compel positive charges to move around this way. But this is literally an open circuit. It's literally a circuit that has a hole in it. So in principle, you cannot make a current flow across this, but in practice, you can for a brief period until it reaches equilibrium. And what I mean by it reaches equilibrium is there is a battery here of voltage V. And initially the voltage across here is 0, but once you connect it to a battery, it starts to build up more and more charge until eventually the voltage across this becomes V. And then nothing else continues. So what initially happens is there is something equivalent to current flowing across this hole, but it's literally not exactly current. It's more the positive charges building up here, repelling the positive charges that are on here to go away and making the negative charges on this side to come in until the voltage across them reaches the voltage of the battery. So that's how the capacitor works. As I said, the capacitance is the charge that you find on the capacitor for a given voltage. So there's a lot of different values for a given capacitor, but once you put a certain amount of voltage on it, it's going to get a certain amount of charge given by this relationship between the capacitors, charge and voltage. Similarly, you can put a certain amount of charge on it, and the capacitor is going to then dictate what the voltage would be, or vice versa. Okay, so let's look at our first case. Let's look at the simple case of a parallel plate capacitor, and I'm going to draw it big and awkward so we can see the geometry of it a little better. Okay, so we're looking at 2 plates. This is going to be an area A. This is also going to be an area A. And in fact, what we'll say is this has a charge per unit area of plus sigma, and this one has one of minus sigma. And I'm going to assume it's connected to a battery of voltage V, this being the positive side, this being the negative side, like that. Okay. What we learned, since this distance right here is going to be really small, D is way, way less, say, than the square root of A. Then we learned for a plate, the electric field for the positive plate, which would be this guy, would in fact, if I draw my coordinate system like this, make this the positive x-axis and make this the y-axis, then my electric field for the positive plate would be positive sigma over 2 epsilon naught. Y'all can look that back up from Gauss's law, pointing in the I hat direction, and that's for x greater than 0, but it's going to be negative sigma over 2 epsilon naught I hat for x less than 0. Does that make sense to everyone? A bunch of positive charges right at the x equals 0 is going to compel any positive charges on the right hand side to move to the right. That's why that's in that direction. And if you go to the left hand side, which remember the y-axis is laying right on this plate, so the left hand side is x equal negative numbers, that's going to compel any positive charge to move that way. Similarly, the electric field for the negative plate is going to be attractive on this side of it. So it's going to be attractive on this side, which means that way. So it'll be positive sigma over 2 epsilon naught I hat for x less than D. And it's going to be negative sigma over epsilon naught I hat for x greater than D. Okay, so what we get is, in this case, E positive points this way, and E negative points this way. So E is equal to 0. Notice there's no X dependence on these. So it doesn't matter how far away you are. Similarly, over here, I get E positive pointing this way, and I get E negative pointing this way. So for this side, I get E equals 0 as well. But inside, that's the cool part. We got E positive pointing this way, and we got E negative pointing this way as well. So in fact, the electric field between is E is equal to sigma over epsilon naught I hat. Does that make sense to everyone? Sigma over epsilon naught I hat. That's because sigma over 2 epsilon naught plus sigma over 2 epsilon naught gives me 2 sigma over 2 epsilon naught. Does everybody agree with that? Now, you may not remember this, so let me go ahead and just stop for a second, redo Gauss's law to show you that this is the case for, just a plate. So let's imagine an infinitely large plate. So this goes on for infinity this way, and infinity this way, and infinity this way, and infinity this way. And I'm going to put the x-axis here, the y-axis here, the z-axis here, and I'm going to use the closed integral of E dot dA is equal to Q enclosed over epsilon naught. I'm going to use Gauss's law to solve that. So by symmetry, I hypothesize, so this is a sidebar here. I'm going to break it off from this with this little thing. So hypothesis. The hypothesis is that the electric field above the XY plane is pointing upward, and I want to think it might be a function of Z and Z only, and it will point in the K hat direction for Z greater than 0. And I think it's going to be the opposite. And by symmetry, it's exactly the opposite because E of Z has to have the same form whether you're above or below it. So it's still going to be E of Z and still times K hat, but it'll have a negative in front of it because it's got to point down. And that's for Z less than 0. Does that seem like a reasonable hypothesis for what the electric field symmetry of this would cause? We don't expect. Go ahead.
How is it only dependent on Z?
Okay, so if you want to argue that maybe it depends on X, well, then you would say, okay, well, that means it's going to have some component, say, in the negative X or the positive X direction, let's say, due to this particle right here. But by symmetry, this goes on forever both ways. So there should be a diametrically opposed one here that's going to cancel it out, any component of it out that way as well. So you definitely don't expect to have it have a Y component nor a X component for the same reasons, because obviously this one would cause an X component and then this one would cancel that X component out. And then that's always going to happen because they're infinitely large. But not only that, because you're no closer to the end, no matter where you are, every spot looks identical to every other spot. And if it had an X dependence, then that would have to be coming from X not looking like the same X it was somewhere else. So that's sort of the symmetries that we're going on. And we're actually going to find out with Gauss's law that it doesn't even depend on Z. Because think about it, if this thing really is infinitely large, if you're 1 meter away, it looks infinitely large. Like you're going to have to turn your head 90 degrees up to try to see the end, and you still won't see the end. And you'll turn your head down 90 degrees to see the other end. You're still not going to see the end. Do the same thing left and right. Now you say, okay, well, let me back up a little bit. Instead of me being 10 meters away, let me go 1,000 meters away. Well, guess what? It's still infinitely large, so it's still going to look the same. So you wouldn't expect it to matter how far you are away from it, because it's always just as much crap in front of you to begin with. So that's sort of another way I like to think about it. Did that help you? Do you see that a little bit? How one, it can't have an IJ component, and two, it can't depend on anything other than Z?
Yeah, that helped a lot. Thank you.
No problem. All right, so left-hand side of Gauss's law, closed integral E dot dA. Well, I've got to choose a Gaussian surface. I'm going to choose a cylinder. And the cylinder is going to come down, and then it's going to pierce the front surface and go to the back surface back here. Okay. And this top part is going to have an area A, and this bottom part is going to have an area A. So dA for the top is going to be equal to dA k hat, because it's always got to point out of the volume. So that's going to point straight up above that. So that's for the top. dA bottom, on the other hand, is going to be dA times negative k hat, because that's got to point down. And then this looks like a soup can to me, so I'm going to say this part's the soup label. So I'll say dA for the soup label is going to just be dA, but in this case, it's going to be in the r hat direction from cylindrical coordinates. In other words, it's going to depend on theta and just be made up of i's and j's. Because you can look at it this way and you see, like, for instance, this might be my little surface area, and dA would have to point along a line coming from the center of the system out that way. So that would be the dA for the soup label, is that little structure. And yes, you probably recognize it as RD theta times DZ, because DZ would be the height and RD theta would be the width. But I don't need you to know all that. You just write dA and it'll be fine. Okay. So now I'll get the integral over the top plus the integral over the bottom plus the integral over the soup label. And when you get this, you're going to get the integral over the top. Well, over the top is a constant Z. So that's just going to become E of Z. Let me give myself more room on this. Since it's a constant Z on the top, we're going to say it's just E of Z that can be pulled out in front times the integral of K hat dotted with dA K hat. Right? Because we're doing the top, and dA K hat is the top one. Plus, in this case, I'm going to have negative E of Z integral K hat dotted with negative dA K hat, because again, the bottom has a negative dA K hat for it. And then plus the soup label, which in this case, the Z is going to vary. So it's actually going to be E of Z K hat. And it's actually going to be plus or minus, because up here it's going to be plus and down here it's going to be minus. But luckily that doesn't matter, because it's going to be dA R hat here. And of course, this becomes K hat dot R hat is going to ultimately equal 0. So that won't matter. So you'll have the E of Z plus or minus. You've got to evaluate that at all the Z's, and the dA is going to have some Z in it. So you got to integrate with respect to dZ. But because all of that's going to be multiplied by K hat dot R hat, this whole integral is 0. So that's the soup label integral is 0. This one, on the other hand, I think you can see it's just going to become E of Z times A. And this one's going to become negative E of Z times negative A. So we end up getting 2 E of Z times A. That makes sense to everyone? All right, now we're going to do the right-hand side, which is super easy. The right-hand side, Q enclosed over epsilon naught is just going to be, basically, I said, like I did over here, I said there's going to be a charge per unit area sigma. So we're just going to call that sigma A over epsilon naught. Left-hand side equals right-hand side is going to give us now 2E of ZA is equal to sigma A over E, or epsilon 0. Those A's cancel out, and I find that E is in fact going to be equal to sigma over 2 epsilon naught K hat for Z greater than 0, and negative sigma over 2 epsilon naught K hat for Z less than 0. And that's fully what my hypothesis was. And basically, it's just showing that E of Z has no Z dependence. So you can see that's exactly what I used up here when I was calculating the electric fields between the plates. I used the fact that the positive plate is always going to have the electric field pointing away from it. So over here, between the plates, the positive plate is pushing that way, but the negative plate on its left-hand side is acting attractive. So the electric field for it between the plates is also this way. So those two added in between to give me sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which gave me just sigma over epsilon naught right here. Over here, the negative plate still pulls this way, but the positive plate pushes that way. So they're going to cancel each other out. And the same thing happens over here. In this case, the negative plate pulls this way and the positive plate points that way. So they get an E outside of 0. So now hopefully you fully understand why the parallel plate capacitor has that. Now, again, we are actually using this for distances small compared to the distance to the edge. Obviously, we're going to have some error in that, but luckily we find that there's very little error for not taking that into account. The vast majority of the area is far from the edge. Therefore, the capacitance comes out to be pretty accurate when we derive it this way. So that was another opportunity for you to see Gauss's law. And that's why I told you we spent such little time on the Gauss's law chapter, because the rest of the book is going to have a lot of time dealing with Gauss's law. So now what I need is, remember, capacitance is equal to charge divided by voltage. I can calculate the voltage from one plate to the other using our definition of voltage, negative integral E dot dl. And then I can take Q and divide it by it, and that will give me the capacitance. So now that I have the electric field, which I derived via Gauss's law, I can now use the electric field to calculate the voltage. So I used Gauss's law to calculate the E field. Now you don't always have to do that, but hopefully that's the easier of the ways, is using Gauss's law. So hopefully you can use Gauss's law to do the electric field. Otherwise, you have to do that integral stuff we did with Coulomb's law. But in this case, I use Gauss's law to calculate the E field. Now I will use V, delta V, is equal to negative integral of E dot dl to, well, why don't I keep writing TH instead of TO, to calculate the voltage difference between the plates. Okay. So I've got my plates here. I'm just looking at them in the coordinate system that I drew up there. So I'm going to repeat all that again. So here's my x-axis and here's my y-axis. And my plate is going to be blue like I drew it before. Okay. And then I'm going to have another plate right next to it. And this is at a distance d away along the x-axis, of course. And you can see in 3 dimensions, it looks basically like this. Okay. I'm going to assume this side is the positive side and this side is the negative, and it's going to have a charge, of course, of plus Q. Now, what I want to do now is calculate delta V, and I'm going to call this A and this B is equal to VB or VA minus VB, which equals a negative integral of E, which we now know is sigma over epsilon naught I hat, right? Actually, it's going to be sigma over epsilon naught. Yeah, positive charge is going to want to run that way, so it will be in the positive direction. Dotted with DL, and DL is going to be DX I hat. So I just chose the positive coordinate direction for my DL. That means I've got to use the direction I'm going to indicate, be indicated by the ranges of integration. So I'm integrating from x equals 0 to x equals d. By doing this, I'm going from high voltage to low voltage, so I should get, in fact, a positive quantity. If I don't, that's okay, but it's really good practice for you to always try to get a positive quantity so you can better understand voltage. But if you don't have to redo the problem. You just drop the negative sign and use it anyways. So now what I'm going to do is I'm going to get a negative sigma over epsilon naught. Of course, I hat dot I hat's just 1, and I get the integral dx from 0 to d. And I got that. What was this sigma? It's definitely positive going that way. And I did go from A to B, which is the direction of positive charge we want to go. So I should get that. And I did go from 0 to D. That makes sense. Okay. So this becomes negative sigma over E times D minus 0. So for some reason, I got sigma over epsilon naught D. I was really expecting to get a positive. I don't know what I did now. Dx is in the positive I hat direction. That's the way it goes. And yeah, everything looks okay. If the positive plate's there, the electric field should go away from the positive plate towards the negative plate. And I got a change in voltage, which is final minus initial. Oh, duh. I was supposed to be final minus initial, so this should have been VB minus VA. Duh. Notice I went from here to here. So that should have been VB minus VA. I let myself run astray with that. So that should have made this 0 to D to 0, not 0 to D. Wait a second. Final. No, that's still 0 to D. And that should be a lower voltage. Yeah. So yeah, everything I did was right, but I ended up choosing from here to here, which is a lower voltage than I should have. So I actually tried to calculate a negative. I just did it by accident. Okay. So what happens when I chose A to B and wrote it this way, I definitively choose and decrease in voltage, which is obviously going to give me a delta VB and a negative. So as I said, it doesn't matter. You're just going to take that voltage and drop the negative sign. Okay. So now that we have the voltage, the magnitude is just sigma over epsilon naught times D, which, by the way, is just E times D. And that's what we learned before for a parallel plate capacitor. The electric field strength times the D, the distance between the plates, is actually equal to the voltage. Now I'm going to use C equals Q over V to calculate capacitance. So the charge of the capacitor obviously is a charge Q. So that'll be big Q over here. And then the voltage, of course, is sigma over epsilon naught times D. So sigma is actually the same thing as Q over A. We're going to make that change in a second. And we can say this is going to become epsilon 0, because dividing by a fraction means flip it over. So the epsilon 0 comes on top. The D, on the other hand, stays on the bottom. And then the sigma is on the bottom. And Q like that. Now, here's the deal. Sigma is equal to the total charge divided by the total area of the plate. So one plate's whole area. So when you do that, you see, oh, well, C will equal epsilon 0 A over D, because the Q will be down here and cancel out. And in fact, that's a general rule. Notice this only depends on the epsilon 0 and the area and the diameter, I mean, the distance apart. That's the fact. Whenever you do a capacitance calculation, it should only depend on the geometry of the capacitance and perhaps the dielectric parameter, and that's what this is. We did it for air filled, which is essentially the same as a vacuum. So we got epsilon 0. If we'd done it for something in between there, we would have used a different epsilon that represents the material that we stuck in there. So notice the Q's had to cancel out. That's what the actual capacitance for a parallel plate capacitor is. You see that a large area gives you a large capacitance. A small separation gives you a large capacitance. And then, of course, whatever material you use can affect it as well. Any questions on that? So that's the big process. This is that multi-step, what I said was a good university level physics / science problem, where you use either Coulomb's law or Gauss's law to calculate the electric field of some kind of structure. Then you use V equals a negative integral of E dot dl. And that actually allows you to calculate the voltage difference between two parts of that structure. Then you do the total charge on one of those pieces divided by the voltage from those two pieces, and that gives you the capacitance. So that's like a 3-step problem you've got to be able to do. And we usually use Gauss's law to do it, in which case that means you're only going to be able to use it with infinite planar symmetry. So it's got to be flat plates that are very big compared to how close they are together, or they have to be cylinders that are very, very long. In other words, you're only staying away from the ends, or they have to be spheres. So you can deal with parallel plate capacitors, you can deal with cylindrical capacitors, which is like a coaxial cable, and you can deal with spherical capacitors. So everybody follow what we did there now? Again, I used Gauss's law to calculate the electric field. I found out that the electric field was sigma over 2 epsilon naught on each side of the plate. And if the plate's positive, it's going to point away on each side of the plate. So above the plate, it points up, and below the plate, it points down. Then I applied that to two plates next to each other that had a charge of plus Q and minus Q. I found that the plus and minus plates canceled the electric fields outside of the plates, but between them, they doubled it up, which gave us a total electric field in the middle of just sigma over epsilon naught, pointing from the positive plate towards the negative plate. So that was me using Gauss's law to find the electric field between the capacitors. Then I stupidly went from high voltage to low voltage, high voltage being the positive side and low voltage being the negative side, and expected to get a positive, even though I hadn't acknowledged I was going from high voltage to low voltage. So because of that, I ended up getting a negative. I should have done it the other way. Then I would have got a positive. Doesn't matter. The magnitude is going to be the same either way, and that's all you're going to use. So I took the magnitude, which meant just dropping the negative, and I got sigma over epsilon naught times D for the voltage. Then I took the capacitance formula, which is defined to be the charge per unit voltage. So I took the charge and divided by that voltage. And then I got rid of the charge per unit area, sigma, by using A over Q. Or excuse me, Q over A. So the Q down here is in the numerator. That cancels out with that Q. The A down here is in the denominator. That means it's going to come to the top. So I ultimately got epsilon 0 A over D. That's the big process. So let me show you another one just for the heck of it. Let's imagine we have a coaxial cable now. And I'm going to again orient it so that I can make use of some nice coordinate systems that we have. So what I'm going to do is I'm going to say, that's my z-axis. This is my x-axis. This is my y-axis. And this is my z-axis. Now what I'm going to imagine is that I have a cylindrical charge distribution that goes on for infinity both ways. And concentric with that is another charge distribution okay. I'm going to say this is a radius R1. I'm going to say this is a radius R2. And I'm going to say this is a radius R3. I'm going to say rho for the inner one is equal to a constant. And that is in fact plus Q over pi r squared L. And I'm going to say for the outer one, we're going to have a surface area, or excuse me, a surface charge sigma, which is actually the inner surface, which equals negative Q over 2 pi r L. And that's 2 pi r. This one should be pi r1, and this one should be 2 pi r2. Okay. So again, I'm going to use Gauss's law. And I'm going to actually calculate the electric field for R less than R1, for R between R1 and R2, and then all the way out to R3. Okay. Well, actually, I'll probably just stop at R2. So what is the electric field for R less than R1 and for R, let's say R1 less than R is less than R2. Okay. And this is going to be a conductor. So first off, I'm going to say R less than R1. I'm going to create a Gaussian surface. I shall make it green this time. And I'm going to say, okay, my Gaussian surface should be a cylinder like that. I'm going to say this length right here is L, and I'm going to say this radius right here is R. Okay. So doing that, I take the left-hand side and I make a hypothesis. I'm going to say E is equal to E of R pointing in the R hat direction. So that forces the closed integral of E dot dA, excuse me, the closed integral of E dot dA. That's going to make that equal to the integral of E of R hat dotted with dA R hat. That's for the soup label portion. But then I have plus integral E of R hat dot dA K hat plus integral E of R hat dot dA with a negative K hat. This is going to be 0 and this is going to be 0. Everybody recall why that's the case? These two being 0?
90 degrees to each other.
Exactly. The R hat and K hat are 90 from each other. So that gives me, since we're at a constant R, the E of R comes out in front, the R hat dot R hat is just 1, and the integral of dA is just the area of the soup label. So I say E of R times 2 pi R L. The right-hand side is obviously Q enclosed over epsilon naught. So I will say Q enclosed is equal to the integral of rho dV. Well, what I'm going to use for my differential air volume element is a cylindrical shell, if you will. So I'll say it's equal to rho, which is a constant, times the integral dV. And the integral dV I'm talking will be, let me draw it right here. So basically this is R. This distance from here to here is dr. This distance is L. So I'm going to say that's 2 pi R times dr times L. So 2 pi R dr times L, like that. Does that make sense to everyone? 2 pi R is the distance around here. So if I imagine cutting this straight down here, it would lay down like a thick little slab, if you will, like this. But the thickness is only differentially thick. This length would be 2 pi R. This length from here to here would be L. This would be 2 pi R plus dr. But again, the difference between that and this cube, which would be 2 pi R times dr times L, the difference is just these little parts, which are on the order of dr squared or higher. So that's why it's okay to use this. So this becomes 2 pi L rho times the integral of RdR from 0 to R1, actually to just plain R. So I'm basically doing the gory part now. You could actually have worked out a nice little formula where you didn't have to do any of this integral, but I'm doing the integral so you can see how it would be done if you had to. For instance, if I gave you that rho was not a constant, it was some constant times R, this would be what you'd have to do. You don't actually have to do that for this one. I'm just showing it to you in case you want to or need to later. So now I've got that. The integral of RdR is 1/2 R squared. So I'm going to get 2 pi L rho times 1/2 R squared, evaluated from 0 to R. And it's not that obvious that that's R up there, so I'm going to write it better. Okay, so this becomes pi R squared L times rho. And of course, rho, we know what that is. So we get pi R squared L. Rho is Q over pi R1 squared L, or excuse me, big L. So you can see the pi is going to cancel out. And basically what I get is Q R squared over R1 squared times, oh yeah, this L was supposed to be in the bottom. I don't know why I wrote it up there. Times L over L. That might seem weird, but you're going to see what that comes into play later. So that's ultimately what all this stuff is that's just going to become this quantity here. So left-hand side equals right-hand side is just E of R times 2 pi RL is equal to, that was just Q enclosed, so I still got to divide it by epsilon naught. So that's Q R squared L over epsilon naught R1 squared L. This L and this L clearly cancel out. These two cancel out, leaving 1 with that one. So I get E of R is actually equal to Q R over 2 pi epsilon naught R1 squared L. That's the really the way you can think of this is the electric field per unit length is another way of thinking about it if I multiply by L or something, but it's going to come in handy when we consider basically the capacitance per unit length. This little L down here will make perfect sense. You can see it sort of looks like it did before, but notice now the dependence is linear. So that gets us just to R, but luckily that's not the part we need. What we now need is for R between R1 and R2. So now I'll say R1 less than R less than R2, like this. And now I'm going to draw a different Gaussian surface. I'll do this one in black. But it's going to be the same shape as the last one. Oh, excuse me. I did do 2 of them for some reason. I was making up the differential volume element instead of the actual Gaussian surface. So this is out a distance R. That is a length L. So the closed integral E dot dA equals Q enclosed over epsilon naught is going to be used again. So the left-hand side is going to become the integral, again, making the same hypothesis, E of R, R hat dotted with dA, R hat, plus 0 plus 0, for this is the top and the bottom. And this is the soup label. Okay. So in this case, I'm going to get equals E of R times 2 pi R times L. Again, that's just the surface area of, or basically it's the area of the soup label, because its length would be 2 pi R and then its height would be L. The right-hand side is easy peasy because it's Q enclosed over epsilon naught. Well, Q enclosed for this is just the total charge Q on the inside. So that's just going to be Q over epsilon naught. So I'll say left-hand side equals right-hand side. And I get E of R times 2 pi R times L is equal to, now it's technically not L, excuse me, I shouldn't say it's technically not Q. Q is the total charge of an infinite length. So really what it is the charge per unit length times the actual length. So if I multiply the charge per unit length times the actual length, then I'll get this. Does that make sense? Well, in this case, it'd actually be the little L. So I'll say it's going to be Q times L over pi R1 squared big L. So I'm going to say this side is QL over pi epsilon naught R1 squared big L. These L's cancel out. And I'm going to get E of R is equal to Q over 2 pi squared epsilon naught R1 squared R times L. And that'll be, of course, in the R hat direction as we hypothesize. So this is for R1 less than R is less than R2, which is really what we need to do the capacitance. Anybody have any questions on that? That was a really complicated one, but again, I was trying to make it complicated so you can see what happens if someone gives you a row, or if you're just not prepared enough to figure out how to relate the total charge to the fraction of the charge that you're using inside of your Gaussian surface. What you normally do is say, okay, well, this is a constant. So the total charge is the Q over the total area, which obviously are over the total volume, which is pi R1 squared L, where L is going to be infinitely long. Well, you can say that's equal to the little charge that's inside over pi R squared little L. And then, you can set those equal and then solve for the little q that way. That's nice as long as it's constant, but if it's not a constant, then you have to do this brutal integral stuff. So really the right-hand side of Gauss's law is the one that turns out to be sometimes more difficult. So we've done all that, and I was just showing you how you could do it for the inner part as well. We didn't really need this inner part at all for the actual calculation of the capacitance. So now what I'm going to do is I'm going to use this electric field to calculate the V. So what is delta V from, and let's try to do positive this time. I called the inner one, did I call it positive? Yes, I called the inner one positive. So I'm going to say from outer to inner. That's supposed to be two N's. It looks like I just made an M instead, like I negotiated it. So delta V is equal to V final minus V initial is equal to negative integral E dot DL. Okay. So that's really what we're using. I am going to integrate from R equals R2 to R equals R1, because R2 is the negative plate and R1 is the positive plate, so that'll cause an increase in voltage. So delta V is equal to negative integral. Now the electric field is going to be Q over 2 pi squared epsilon naught R1 squared RL. And that's R big L, sorry about that. And then the R hat direction. And then I'm going to use the positive coordinate direction for my dl, so I'll write dr r hat, and that means I've got to use the range of integration to dictate which way I'm going. So I'm going from R2 to R1. Okay. Now, really, this is a big, ugly mess, but to be honest with you, the only part we're really integrating is dr over r. All this other stuff is just constants that don't really matter. So I'm going to get negative q over 2 pi squared epsilon naught r1 squared L times what we're going to do now is the natural log, because of dr over r, the integral of that's r to the negative 1. If you added 1 to it, you get a 0. That doesn't make any sense. So that should remind you, oh, that's the natural log. So I'm going to do the natural log of R1 divided by R2. Because you do R1, ln of R1 minus ln of R2. And remember, the subtraction of a ln is equal to the ln of the quotient. In other words, I'm using ln of A minus the ln of B is equal to the ln of A over B. Y'all remember that from grade school? My PhD advisor used to say, we know that all the way from kindergarten. We did not know that from kindergarten, obviously. All right, so now we've got that, and that's kind of helpful. That's actually my voltage. And in fact, you can get rid of that negative by flipping it over. And notice R1 being smaller than R2 is going to actually make the natural log a negative number. So by absorbing this negative and flipping it over, I actually do get a positive amount. So the delta V is in fact equal to Q over 2 pi squared epsilon naught R1 squared L times the natural log of R2 over R1. Now I can say C is equal to Q over V, and per unit length. So that's the next question. What is the capacitance per unit length? I know you can't read that. That's why I'm reading it out to you. And that's really what happens if you buy a coaxial cable, which is really what this is RG, I think they call it RG6 and RG59 or something like that. One's cheap, the other one's a little bit better. But the main thing is that outer wire housing that's sort of braided, that's one of the terminals. And then the inner core metal is the other terminal. And that's actually carrying a current. And depending on how many feet you use, you get a certain amount of capacitance due to that wire. So I'm ultimately going to calculate C, but then I'm going to do C per unit length, and that'll make some sense in a second. So now I'm going to say C is equal to Q over 2 pi squared epsilon naught R1 squared L times the ln of R2 over R1, which might seem really crazy, but notice, as I told you, it's only supposed to depend on the geometry of the capacitor and not the charge. So the charges did cancel out. And what we ultimately get is 2 pi squared epsilon naught R1 squared L over the natural log of R2 over R1. And notice, if you want the capacitance per unit length, you get rid of that L and just put it under here. So you divide both sides by L, and that gives you capacitance per unit length. But that's plenty enough right there. Any questions on that? So yeah, that's the big paradigm that we expect you to accomplish in this 242 course. We expect you to be able to take a symmetric charge distribution that can be solved with either Coulomb's law or Gauss's law, use that to calculate the electric field, then calculate the electric field between a positive part and a negative part, and use that to calculate the voltage from the negative part to the positive part. So it'll come out positive, and then divide that charge by the actual voltage, and that'll give you the capacitance. So in this case, if you wanted capacitance per unit length, it would be this formula right here without that L line. That's what I was telling you, where that L will actually come in handy later. If you actually, they used to just print it right on the coaxial cable. You could go to like Lowe's or Home Depot and go look at the coaxial cable, and it would say a certain number of ohms per meter or ohms per foot. And then it would say a certain number of farads per meter or farads per foot. Now I've noticed that I don't see them marked on it anymore, but you can go to the website for the company that makes it, and they'll tell you how many ohms it has. It'll also tell you how many henries it has, which is what we're doing next. Once we study the magnetic field, we can then do a similar process to what we just did. Instead of using Gauss's law, we'll use Ampere's law. And instead of calculating an electric field, we'll calculate a magnetic field. And then instead of using that electric field to calculate a voltage, we'll use that magnetic field to calculate a flux. And then we'll take the flux and divide it by the current, and that'll give us the inductance in henries. So it's the exact same sort of process, but it's one dimension down, because instead of doing a surface integral, you're going to do a line integral for Ampere's law. So that's the total result. If you actually look at it, your book probably does one like this. In fact, yeah, I see their example 24.2 is just like this. What they have different, though, when they ultimately get it, is they get a 2 pi epsilon naught L over the same len that I do. So the reason why they don't have a squared pi and a squared R1 is because I use that ultimate formula with the pi and the R1 squared. I use that to calculate the total charge of a section of the wire. So it's the same problem they did, except mine was allowing you to see how you would investigate a cylindrical charged object with Gauss's law. So hopefully that extra generalization made it a little more complicated and helped you understand a little better how to attack Gauss's law in weirder situations. So it's 6:08. That's essentially time for class to stop. 6:10 is the real time, but anybody has any questions, you're welcome to stick around and ask me. Otherwise, you're free to go, and I will see you guys again. Today's Wednesday, so I won't see you guys again until lab tomorrow at 1:30 or for lecture on Monday, weather permitting. Don't forget to do your tests, everybody. Remember, online tests. Don't forget it. Online test due by Sunday. Tell a friend.
All right. Good night.
Good night, Nicholas. Or, oh, I thought it was Nicholas talking. Might not have been.
Yeah, it was.
Okay. Anybody have any questions? I'm here, to help you. This was a lot of stuff y'all covered tonight, so it might have been scary. Gerald or Shimon, do y'all have any questions?
No, I'm good.
Okay. Well, I will let you
I'm
go.
good.
Have a good evening.
Have a good evening.
Bye-bye. Gerald, did you want to say something? Nope, he's gone.